All right, let me do that again. Good evening, everyone. This is week 5 of our lecture. So last time we covered material about vectors and their components and like the definition of the vectors, like their initial point, terminal point, and how the initial point plus the vector is the terminal point. Some basic properties about addition, components, of multiplying by numbers. We went over some examples. And we covered this notion of a norm. Also, we talked about the angle of the some vectors and we went over some application problems. Yeah. So let's start off with like some similar review of these exercises. Right, you can also message me if you get the answer. Well, or Franklin or Jonathan. Alright, let me just check the chat. There's a bunch of people sending me stuff. Alright, let's go over some of them. Alright, let me ask some people. Alright, Ethan, what did you get for question 1?
Root 41.
Good job. What? Alright, question 1 is root 41. Alright, question 2. Ifan, what's the answer to number 2? Alright, let me ask someone else then. Let me just go over it. Well, so for this one, you just look at them one by one. So let's say we do this one first. Do like the multiplication steps first. So this is negative 1, 6 minus, well, technically you can do minus 2 and you distribute negative 2 inside, but I'll do minus negative 12, 4. And we'll minus again 0, 12. We just evaluate this. Minus 1 minus negative 12 is 11. Well, technically minus 0, but it's still 11. And 6 minus 4 minus 12 is negative 10. So the answer is 11 minus 10 for question 2. Debo Priya. What's the answer to 3? Maybe I pronounced your name wrong. I'm sorry. I guess I'll just go over it then. So this, using the definition, is the product of the top two plus the product of the bottom two. So this is minus 10 minus 12, which is just negative 22. And for this one, you technically have 2 ways to do this one. I'll do it in one way first. Actually, I'm going to go over both ways. So here we have, the first way is we just find u minus v and then find u plus v and then multiply them using a dot product together. So u minus v is 5i minus 12j and then minus 3i plus 4j. So this is 2i minus 16j, or we can write 2 negative 16. Dot product, we have u plus v, which is 8i minus 8j, or 8 minus 8. We can do dot product, these numbers together. So you get top is 16 and bottom is 128. So 16 plus 128 is 144. That's way number 1 to do it. All right, so the answer to this one is 144. The other way to do it, it's more interesting. When you look at the distributive property on these two things, it's just like multiplying with normal numbers. So let's do it step by step. So this is u times u plus v, u dot product u plus v. And then minus v dot product u plus v. And this is u dot u, which is u norm squared, plus plus u dot v, minus v dot u, which is technically also u dot v, and then plus v dot v, which is v norm squared. We look at the u dot v's, they cancel. Oops, I'm sorry, this is negative. So the u dot v's cancel. And the answer will be u norm squared minus v norm squared. U norm squared is 5 squared plus 12 squared is 169. So this is 169 minus v norm squared is 3 squared plus 4 squared is 25. This is 169 minus 25, which is also 144. So here are the 2 ways to do it. You might see this usage in some of the other problems today, maybe in the homework as well. All right, the unit vector question in the homework, you can notice that because we just calculated v has norm squared of 25, so that's norm 5. So v norm is 5. We notice that v has like norm 5, or like the length is 5. So we shrink it by like 1/5. We get a unit vector, which is a vector of unit length, or length 1. So the answer will be v over 5. Or if you write it out explicitly, 3/5, 4/5. I can't write today. All right, for question 5, you just like go over all the pairs or something. You just go over all the pairs, you can eventually find that these two work because 36 minus 36 is 0, and you get that these two also pair up. And also, well, interesting fact, well, not that interesting, but two vectors are orthogonal actually means that they're perpendicular in the xy plane. So if you plot out 4, -6, maybe it's like 4, -6, maybe it's like this. And we have 9, 6, maybe like something like that. So if you plot these two vectors together, we actually get this is a right angle over here. Same for these two. It's another geometric interpretation of this result. Wait, let me just like set off my pen though. Sorry, I need to pause the sharing for a bit.
Okay. I guess we'll talk about independent vectors right now. So let's say we have some collection of vectors, A1, A2, all the way to AN, and we call them independent if like there's no way to choose some constants x1, x2, all the way to xn, such that they're all non-zero. So basically it's independent if the only solution is just all zeros. And in two dimensions, any set with one non-zero vector is independent because if xn is like anything that's not zero, then the sum would be non-zero, which means it would fail this condition. And the set of two vectors a, b is independent if a and b are not multiples of each other. And a set of three or more vectors is always dependent. This should say in two dimensions. And we just call the vectors dependent otherwise. That's pretty easy to remember. And there is a special case since that the vector zero vector is dependent with any other vector because you could just let the zero vector's constant be like one or something and all the other ones be zero. All right, does that make sense? Okay.
Okay, so here we have some geometric interpretation of the dot product. So we start with the law of cosines, which says that in a triangle ABC, so we start with the law of cosines, which says that in a triangle ABC, c squared equals a squared plus b squared minus 2ab cosine of c. So to get this expression, let's plot this in a coordinate plane. And theta denotes the angle between vectors u and v. So we're going to graph vector u and vector v from the start of vector u, from the end of vector u, I mean, so that this vector is u plus v by the parallelogram rule. Okay, so if we just okay, so to find this angle, we can just draw another vector v here. And since both of these are vector v, then these two are parallel. And this angle is defined as theta, which means that this angle here is 180 minus theta. So we can now use the law of cosines on this triangle. So this length squared, or the norm of u plus v squared, equals this length squared, or the norm of u squared, plus this length squared, or the norm of v squared, minus 2 times the norm of u times the norm of v times the cosine of this angle, which is 180 minus theta. So now we have this expression, and we're going to relate this to dot products by using the norm property, or the norm of v squared equals v dot v. So if we put that in here, we get u plus v dot u plus v is equal to u dot u plus v dot v. Okay, now we know that from trig identities that the cosine of 180 minus theta equals negative cosine of theta. So these two negatives are just going to cancel out and make a plus. So this is just plus 2 magnitude u magnitude v times cosine. Let me make some more. Let me erase this. Plus u 2 magnitude u magnitude v cosine of theta. So now we're going to use the distributive property on this term on the left, which is going to be u dot u plus v dot u plus v. And if we use it again, we get u dot u plus v dot v plus u dot v plus v dot u. And we know u dot v equals v dot u from last class, so this is equal to u dot u plus v dot v plus 2u dot v. It's really similar to expansion in real numbers. So this equals u dot u plus v dot v plus 2 magnitude u magnitude v cosine of theta. So that means we can cancel out u dot u plus v dot v, and then cancel out a factor of 2 to give us u dot v is equal to the magnitude of u times the magnitude of v times the cosine of the angle between them, which on this plane is this length times cosine of this angle.
All right, so applications of the previously discussed thing, the u dot v equals to u norm times v norm times cosine theta thing. So we have u equals ab, and v equals cd. We can write the thing we wrote as u dot v is equal to, rewriting it, is u times v, both norms, and then times cosine of theta. So u dot v is ac plus bd. U norm is root a squared plus b squared. And similarly for v norm. And we have cosine theta. So maybe you remember from your trig stuff that cosine theta is always between -1 and 1, inclusive. So this thing over here will have absolute value less than 1. So if we like make it, well, we can have this. Because cosine theta, well, if you do absolute value on this, then this cosine theta part, it has like absolute value less than or equal to 1. So like we can just say that it's less than or equal to 1 times this thing over here. And if we square both sides over here, we get ac plus bd squared is at most a squared plus b squared c squared plus d squared. Right, this is called the Cauchy-Schwarz inequality. It's written like this. And we can look at the equality case for this inequality. So basically, the only time cosine theta has absolute value exactly 1 is if theta is equal to 0 degrees or 180 degrees. Right, equality. So if we like look at this in an xy plane, If two vectors have 0 degrees, they lie in the exact same direction. If they are on opposite directions, they have 180 degrees. So either like that or like that. So these are equality cases. So basically, they're dependent because they, as we said before, one of them is a multiple of the other one. All right, two vectors are two-dimensional non-zero vectors are dependent if and only if one of them is a multiple of the other one. And this, well, this is your inequality right here. For example, if I have 1, 2, say A, all right, erase this. If you have U equals 1, 2, let's just say like AB equals 1, 2, and CD equals to 2, 4. We can plug it all in. So AC plus BD is 2 plus A is 10. 10 squared is at most. A squared plus B squared is 1 plus 4 is 5. And C squared plus D squared is 4 plus 16. So this is 5 times 20, which is also 100. So this inequality holds when they're dependent. This is very interesting because if you have multiple dimensions, well, we didn't talk about multiple dimensions, but like the law of cosines like still works. So if you have like more variables, if you have like maybe E plus BF plus CG plus DH, and then all squared is at most A squared plus B squared plus C squared plus D squared, E squared plus F squared plus G squared plus H squared. Something like this also holds for more numbers, but we don't need to know about this. This is just interesting fact, but like this is very, very important, I guess. It's very important. But something like this also holds. Yeah.
All right, so for these problems, the important formula to keep in mind is that U dot V is equal to the magnitude of U multiplied by the magnitude of V times the angle between them. And if you don't know how to find the angle between them, the easiest way is probably just to plot them. And if that doesn't work, try using law of cosines. Wait, actually, sorry. Wait, you're supposed to find the angles. So yeah, just I guess either give me the angle with like the inverse cosine function or just use a calculator. Oh yeah, and you can DM me the message. And theta should be between 0 and 180 degrees or 0 and pi. Yeah, okay.
Well, I don't think you can DM Franklin, but you can DM me the answer. All right, actually, you can DM Franklin now. I just changed the rules.
All right. I'm gonna start going through the solutions now. I mean, the first one is pretty obvious what the angle is. I mean, the angle is obviously 90 degrees or pi over 2 by just looking at it. But using the formula, the cosine of theta would be equal to dot product, which is 0, over the magnitudes, which is 1 times 1. And this is 0, and we know we can just plug in pi over 2 or 90 degrees here. I'll just use degrees, I guess. For the next one, it's just the same thing. And just make sure to take the inverse cosine. I think no, I think your calculator will always give you a value between 0 and pi. I think that's standard. The next one's actually kind of interesting. If you after we find the answer, but anyways, the dot product is 1 times 2 plus 3 times 1 over root 10 times root 5. So this is equal to 5 over 5 root 2. And some of you might recognize that this means it's 45 degrees. So it's actually exactly 45 degrees, and we don't have random decimals or whatever. This is pretty standard. And this last one, you might see that the second one is a multiple of the third one. First one specifically, it's 3 times the magnitude in the same direction, so the angle is obviously 0 degrees. But if you just want to double check to plug it into the formula, then you'll also find the same result. All right. Does that make sense for everyone? Okay. Jonathan will present the next slide.
Yeah, okay, so here we just have a definition of the projection. So a projection of a vector u onto a vector v is the vector that is in like parallel with vector v, and the endpoint the line connecting the endpoint of the projection and the endpoint of u is perpendicular to vector v. So as you can see here, it's basically just taking the endpoint of u and taking the altitude from it onto the end vector v. And obviously vector v cannot be the zero vector because otherwise it doesn't really have a direction. But projection works as long as v isn't zero.
Alright, so I'm going to give us definite formula for a projection. So let's say these two vectors are u and v, well, as we said before, and their angle between them is theta. So from a geometric perspective, the length of the projection, or this blue arrow, if you draw this right triangle over here, it's just u, well, length of u times cosine theta. And we just learned what is cosine theta. Cosine theta is exactly the u dot v divided by u norm times v norm. So this is u dot v over v norm. Yeah, like right here. And because this blue arrow, well, this is technically a number. So we want to make this not a number instead of vector because we want this direction. So we need to scale it to the correct length of adding a unit vector. Okay, adding a unit vector to the length of the blue arrow. So the actual projection of u onto v is u dot v over v times the unit vector in v, which is v over v norm. So this is u dot v over v norm squared times vector v. Or maybe in other ways, this is u dot v over v dot v times v. But this is like technically the standard formula. So we have the formula over here. Maybe it takes 30 seconds to memorize it. This is a more complicated formula. Notice that here in the end, it's not a dot product and it's a multiplication. All right.
Okay, yeah, I'm sorry, this is more problem spam, but I'll write the formula here just in case you need it. And if you have like any answers, just DM me. Okay, I'm gonna go over the answers now. There's like for the dot products on the top and calculating the magnitudes, I'm not gonna show that since um if you've done the homework, that should be pretty familiar to you. I'll just show like the rest of the calculation. So for part A, it would be 2 over 8 multiplied by this vector. Should have gone 1/2, 1/2. Part B is yeah, if you want to take like a screenshot or something, this is probably a good time to. I'll erase this shortly. Um, just remember that the top is the dot product of the two vectors, and the bottom is the vector that's being projected on. And since we know how a projection like this blue vector, it should be in the same direction as the vector being projected on. So that's why this V term is here because we're projecting onto it. So it must have the same direction. Well, this part gives us the magnitude. All right, does that make sense? All right, I'll go over the next three now. Never mind, next two. And this last one, the vectors are perpendicular. We can see that by taking the dot product, and we find that the dot product is 0. And that means that's going to be 0 regardless. In fact, the dot product here makes us multiply by 0 anyways. All right, hopefully that made sense to everyone.
All right, here before we go on, let's take a break for about 6 minutes. You know, I'm feeling generous, 7 minutes. Alright, now break is over. Send a message in chat. Alright. Here's an interesting problem.
Okay, so we're going to prove the Pythagorean theorem using vectors, which states that the norm of u squared plus the norm of v squared equals to the norm of u minus v squared if and only if u and v are perpendicular to each other. And this is equivalent to the Pythagorean theorem because we know that if this vector is u and this vector is v, then this vector is u minus v. So then the Pythagorean theorem states this length squared is this length squared plus this length squared if and only if this is a right angle. Okay, so first we're going to show that the dot product of u and v being 0 implies that u and v are perpendicular to each other. So this comes from the fact that u dot v equals the magnitude of u times the magnitude of v times the cosine of the angle between them, theta. So we're going to assume that u and v are non-zero, yeah. So if u and v are non-zero, then this is non-zero and this is 0. So cosine of theta is 0. So theta is 90. So that's how we can do part A. So next we can so now we can try part B, expand the norm of the difference squared. Yeah, okay, if you had a chance to think about that. So again, we can use the norm property. So the magnitude of u minus v squared is u minus v dot u minus v. I'm not gonna like just do the distribution. By the distributive property, this is u dot u plus v dot v minus 2u dot v. It's very similar to how we'd expand this if u and v are real numbers again. So if this equals by the norm property u dot u plus v dot v, again, we can cancel this out. So yeah, u dot v is equal to 0. So then part A tells us that u and v are perpendicular to each other.
Also here, if they're perpendicular to each other, it's easy to check that the reverse, then this thing holds is also pretty easy to check. Alright, so here's some like random physics knowledge, I guess. In physics, the general work formula is defined as the dot product between the force and the distance. So if force is F and distance is x, it's F dot x. So here we have this force of 100 newtons, like right here. And we have this ramp of 30 degrees. And this thing is dragged 50 meters up here. So this is 50 meters. Maybe the box is over here now. So we want to find the work done by this force. And some people, in part B, says some people like to use the projection of the force. Maybe I should explain that. So let's say like the arrow I drew already is the force that's not projected. And the force that's projected is basically, we have this thing and we have this projected force is where these are all 90 degrees. And this is our force projection. Maybe I should call it force project, like F proj or maybe. So now we can use the F projection times the distance directly. And we want to check that this is also a valid way to solve these problems. Alright, let's assume that the box doesn't fly off. Alright, just assume this formula works. It's like all frictionless and whatever. If you get the answer for one of them, you can give me the answers, or any of Franklin or Jonathan. Well, I drew a coordinate system at the bottom right corner as a hint. All right, let's go over method 1. So using the diagram I drew over here, we have vector f is, we remember that the vector is the norm cosine theta and then the norm sine theta. The norm is 45 degrees for f. So this is 100 cosine 45 degrees. Maybe I should write it like this. 100 sine 45 degrees. So this is 100 times root 2 over 2, which is 50 root 2. And the other one's also 50 root 2. And the vector x is 50 cosine 30 degrees, 50 sine 30 degrees. So we calculate this, and cosine 30 degrees is root 3 over 2, and sine 30 degrees is half. So this is 25 root 3, 25. And if we do dot product, so work is f dot x, which is 50 root 2, 50 root 2, dot 25 root 3, 25, which is 1250 root 6 plus 1250 root 2. Technically, unit should be joules. And this is about, if you round it to 3 decimal places, this is 4,829.629 joules. All right, let's look at part B now. This is part A. Maybe you want to take a screenshot of this because I'm going to erase this for part B. All right, let me go over part B now. Let me erase this part. Oops, I destroyed the line. Got it again. Alright, the first method is kind of dumb. But like we can use the projection formula. So and in the projection formula we need to find f dot x. So this is really dumb. So f dot x, remember, is 1250 root 2 plus 1250 root 6. So the projection of f onto x is equal to f dot x over x norm squared times x. We literally just used this, so this is really dumb. This is 1250 root 2 plus 1250 root 6 over x norm squared is 50 squared. Actually, you can't write. Yeah, it's 50 squared. And x is 25 root 3, 25. So we just calculate this. This is some number. I don't really want to find this number. This number is not that important because we just find this number times dot x. So we're more interested in the final result, which is this, the norm of this thing times x. Actually, it's this thing dot x because we're still using that formula. But here the interesting thing is that they're actually in the same direction. So we can, like, the angle is 0 degrees. So we can just change this to their norms and their products, because the dot product is equal to the product of their norms and then multiply by cosine theta. But cosine 0 is 0. I mean, cosine 0 is 1, I'm sorry. So this is just the product of these two thingies. And this projection, well, it's this thingy, which is technically, remember that this thing is like, remember that this projection is technically f dot x over x norm times the unit vector x over x norm. And this is length 1. So like this thing has length f dot x over x, this first part. And the second part has norm x norm. So this is just f dot x, which is whatever this thing is already. So like this new method also works. The other, well, better method, instead of using this formula, is we notice that this angle over here, this dot angle, is 45 degrees minus 30 degrees, which is 15 degrees. So we have the projection is, and using this projection is 100 times cosine 15 degrees, and x is 50. So maybe remember that cosine of 15 degrees is root 2 plus root 6 over 4. Maybe you can derive that from angle sum or subtraction as well. This is times 50, and this is the same number. And it's about like 4,000 something again. Yeah, so that's the other way to do it. This is probably cleaner if you look at it directly from cosine 15 degrees. Yeah. Any questions? All right, seems like there's no questions. All right. Oh, I forgot. I didn't even do the projection force. Projection force I already did it. It's over here. It's just 1,000 cosine. It's 100 cosine 15 degrees. This is just 25 root 2 plus 25 root 6 newtons. The direction is in the 30-degree direction, and you just like do the calculation. I just asked for the force, so technically just say the magnitude of the force.
This problem I'll just go over it right now, actually. Actually, no, you should probably spend a bit of time working on it. And it's just prove this expression, and yeah, this hint helps a lot. Just remember your properties of the dot product. All right, I'm gonna first do one of the inequalities. We're going to first show that this thing is true. First, we're gonna square both sides of the equation since we know a lot about these things when they're squared. So for our left side, we'll just expand everything. This is like technically kind of invalid, but like whatever. I'll just do it this way because I don't want to go through it went from scratch the other way around. It's kind of just busy work. And remember that when we have two magnitudes, it's just a dot. It turns into a dot product of the two vectors. So this thing will become, and we just expand the left-hand side as well. And yeah, this is pretty clear. And with the negative, we flip the sign around. So what we need to show is, and what we can do here is we use one of our formulas, which is cosine theta is equal to a dot b over whatever. So one is greater than or equal to. This is, we're dividing both sides by the magnitudes. And we know cosine theta is between 0 and 1, so this is obviously true. I mean, to do an actually rigorous thing, we'd have to go the entire other way around. But this is really annoying. Okay. Any questions? Okay, then I'll do the next part then. So remember, we square both sides again just to make things easier to deal with. And remember, just cancel all of these. So now we just need to show this. Yeah, and we divide both sides by a dot b again. Wait, and this part is just minus cosine theta. And we know that this is between -1 and 1. So 1's always larger than this, and this is always true. All right, does that make sense? I don't know if there's any problems like this in the homework, but it's just nice to know how to write proofs in the future.
I think there might be one problem where you need to do a dot product expansion by like a square of a norm or something. Also, geometrically, this is just triangle inequality. Right, this problem has a lot of calculation, by the way. Jonathan, are you here?
Yeah, okay. All right, so if this is point A, then point B is going to be negative x and 1. Um, point C is going to be positive x2, and point D is going to be horizontal with a length of 2x. And we want angle ABC equals 180 minus angle ADC, which means cosine of angle ABC is negative cosine of angle ADC because of this trig identity. So we're going to start with cosine of ADC since it's much easier. Um, so by the definition, this is a right triangle. So the cosine of ADC is equal to the adjacent side, which is 2x minus x, or just x, divided by the hypotenuse, which by the Pythagorean theorem, this length is 2 and this length is x. So the hypotenuse is the square root of 4 plus x squared. So that's cosine of ADC. Now we do cosine of angle ABC, where we have to use dot products. Yeah. Okay, so cosine of angle ABC is equal to um the norm of vector BA. Oh wait, vector BA dot vector BC over the norm of vector BA times the norm of vector BC. And this comes from the geometric interpretation of the dot product. So vector BA is just the negative of vector AB, so it's x minus 1. And vector BC has a horizontal component of x minus minus x, which is 2x, and a vertical component of 2 minus 1 is 1. And we can find their magnitudes again by using the Pythagorean theorem. And for the top part, we just use the definition. This is 2x squared minus 1. And we want this to equal the negative of x over the square root of 4x plus x squared. So to solve this, we're going to square both sides of this equation, which gives us 2x squared minus 1 squared over 1 plus x squared, 4x squared plus 1 is equal to this squared, x squared over 4 plus x squared. And now notice that every time that x appears in this equation, it is squared, so we can simplify it by letting y equals x squared. Okay, basically all we can really do in this situation is cross multiply. So let me just make some more space on the does everyone understand how we use dot product to find the cosine of angle ABC? So cross multiplying, we get 2y minus 1 squared times 4 plus y squared is equal to, oh wait, no, y isn't squared, sorry. is equal to y times 1 plus y times 4y plus 1. So now we need to expand this out. So the left-hand side is 4y squared minus 4y plus 1 multiplied by 4 plus y. So y times 4y squared is 4y cubed. The quadratic term is 4 times 4 minus 4. So plus 12y squared. The y coefficient is minus 4 times 4 plus 1, so minus 15y. And the constant is 1 plus 4. So that's the left-hand side. And for the right-hand side, the cubic term is 1 times 1 times 4. The quadratic term is y times 1 plus y times 1 times 4y, which is 5y squared. The linear term is y times 1 times 1, which is y. And there's no constant term since there's a y in the front. So then we can cancel out these terms, and the result is the quadratic 7y squared minus 16y plus 4 is equal to 0. So using the quadratic formula, this solves into 16 plus or minus the square root of 256 minus 4 times 4 times 7, which is 112 equals to 144 over 14. So 16 plus minus 12 over 14. So that gives us 4 over 14 and 28 over 14, which simplify to 2 over 7 and 2. Okay, so now we just need to find which of these is correct. So if x is 2, then our diagram is going to look like this. Oh wait, no, okay, if x is 2, then we're going to plug both of them back into our original equations. The angle between the cosine of the angle between BA and BC, I think was this. Um, minus 1. So if we plug 2 back into this equation, then it will simplify to 7 over the square root of 5. If we plug
Squared
root
is
2
2.
back in, oh wait, that was y. If we plug in x equals root 2 back into this equation, this becomes 3 over root 3 times root 9 equals 1 over root 3. But this is positive and this is negative, so they can't be correct. So x squared equals 2 is incorrect. So the answer is y equals x squared equals 2 over 7. So yeah, very complicated problem.
Alright, maybe we wait for a few minutes. Well, this is a pretty complicated problem. You need to check for the extraneous solution in that. Or there won't be like this complicated problem on the homework. If you're not done, just check the recording. Wait, actually, we can wait for some more. Alright, now if you're not done, you can check the recording. Alright, let's look at the last problem. Alright, this one is easier than the previous one. So we have like this triangle thing. We have A, B, C, like distinct points. You draw them. We have A, B, C. And we have O in the middle such that AO equals BO equals CO. And we draw this sort of random point H. It's probably like right here. And we want to make OH satisfy this random property over here. So OH equals OA plus OB plus OC. We want to prove that segment AH is perpendicular to segment BC. Alright, let me just give the hint. So segment AH is perpendicular to segment BC is equivalent to AH dot BC is 0. Alright, now you need to recall like geometric interpretation. Like what is the vector AH? And maybe you can have some time to try that. Alright, let me just give the other hint away. So if you look at the geometric interpretation of AH, which is like this arrow, we can write it as a combination of this arrow and this arrow. So AH is AO plus OH. And BC similarly is BO plus OC. So we only need to prove that the dot product of these two vectors is 0. Wait, I'm sorry. This is not BO mine. This is not. Oh, this is BO plus OC. I'm sorry. Remember that OH is OA plus OB plus OC. Oops. And also, BO is negative OB. Alright, as there's about only 3 minutes left, I'll just finish the problem. So AO plus OA is like sort of like vector AA, which is 0. So the things on the blue arrow cancel. So this is OB plus OC. Dot product negative OB plus OC. And we've done this like 100 times already. More like 5 times. But this thingy over here is negative OB vector squared plus OC vector squared. I think we've done that for many times already. So this over here is exactly 0 because we know that BO equals to CO. So that's how we prove that this dot product is 0. Actually, for similar reasons, BH is perpendicular to AC and CH is perpendicular to AB. So this actually implies that if you learn geometry, H is the orthocenter of triangle ABC. And actually this, well, if you also learn some geometry, this means O is the circumcenter of triangle ABC. So this gives some interesting, well, relation between O and H over here. Also proves the existence of the orthocenter, if you know the circumcenter exists. Well, they do exist. Actually, if you're interested in something very interesting, you can actually prove that if G is the centroid. I'm just here to like point something random out. So if you just want to do this for like an exercise for some reason, people like math or something, you can do like, you can prove this, and in fact this shows that OGH are collinear if G is the centroid. Alright, this is just a digression from today's topic. Alright, this time I will not forget to assign the homework. Alright, today's homework is 27 to 48 multiples of 3 on these 2 pages over here, and also the PDF pages are these, and these 2 challenge problems. Alright, maybe I should talk about how to use the PDF thingy, because I talked about it for many times. So if you go to Alex's like handout over here, like you see this loads like super slowly. So like you can press the print button and like it loads it in like a split second. Well, faster, I guess. There you go, that loads everything. So that's what I'm talking about. Alright. Thank you very much. Yeah, thank you very much.